Okay, we're going to be doing this integral. And this one, 1000%, you do not have to do use substitution. You could literally just distribute here. You'd get the integral of 8x plus 12 dx. And absolutely, you could just apply and get like the antiderivative of this. Oops, so I probably don't need that derivative symbol there. The antiderivative of x is 1/2 x squared plus the antiderivative of 12 is just going to be 12x plus c. So you'd get equals 4x squared plus 12x plus c. 1000% that is okay. But I think the reason that they added it here is that you could treat this like a u substitution. So I'm going to show you what that would look like as well. So we're going to make this the integral of 4 u dx, and in this case u would be 2x plus 3. Du dx would just be 2, and then I'm going to solve here for dx, so I can just replace the dx. So if we then multiply both sides by dx, then we get du equals 2 dx, and then if we divide by 2, we get du over 2 is equal to dx. So I'm going to replace that, and I'm going to say, okay, then I have the integral of 4u, and then du over 2. Those 4 and the 2 are going to simplify, and you just get the integral of 2u du, which ends up being u squared plus c, which, again, then u is just 2x plus 3 squared plus c. Now you might be thinking to yourself like, this and this do not look exactly the same. Like you said I was going to get this, Miss Perkins, but I actually got this. If we expand this, right, if you did like 2x plus 3 times 2x plus 3, and then we still have our plus c, you're going to get 4x squared from that. Here's going to get 6 and 6, so plus 12x, and you are going to have this plus 9 plus c. But here's the crazy thing, and why that plus c actually really does matter here, is that this c could be anything it wants, and it doesn't necessarily have to be the exact same thing this was. So at some point, we're going to have this like core function itself, and it's going to get shifted up or shifted down or something. Maybe over here plus c is 0, or plus c is 9, and over here plus c is 0, but you do end up with the exact same thing. So either method will work for you no matter what you do. If you had some point on the curve where like, and I'm making this up right now, if you said like 1, 0 worked on the curve, then you'd plug in 1 and 0 here and solve for c. You'd plug in 1 and 0 here, and you'd solve for c again, and you would end up with the exact same thing. That 9 would just change a little bit how you'd solve. So, works both ways. Okay, so now let's do b. In this case, I'm going to make this my my u. So I'm going to write this as the integral of 2x e to the u dx. And remember, the thing that you're looking for here is that the derivative of whatever you pick as a u exists somewhere else. And in this case, the derivative of 1 plus x squared is 2x. That's what I'm looking for. So u is 1 plus x squared du dx is 2x. And hey, again, notice like that derivative exists elsewhere. So you have a couple choices at this point. The last one I solved for dx. You could do that, or you could just say, hey, I already see that 2x is there, so let's just replace that one. I'll kind of like jump back and forth in the things that I do here. We're going to replace that with du dx, and then we have e to the u dx, and now it's just a matter of simplifying. Well, the dx's will simplify, they're going to be gone. And even though the du is currently in front of the e to the u, they're just getting multiplied. So again, that's kind of the weird, like, du is simultaneously an operation and part of the equation, which is sort of a weird thing. But now we just have e to the u. I know how to deal with that. That's just e to the u plus c. And then if we replace with u, we get the answer is e to the 1 plus x squared plus c. That is my original function. Okay, cool. Next one. I'm going to make this my u. So we're going to get the integral of 1 over u dx, where u is 2x plus 3. And if I was looking for, the derivative of this is just a coefficient, so I'm going to be able to work this out, so it's not going to be impossible. The derivative, quote unquote, exists because I can just use a multiplier. Du dx is just 2. And so this time, let's actually just solve for dx. So a little bit different than what we did last time, but again, multiple methods. If you end up solving one of these and you end up with the exact same answer as me, but you got it a different way, awesome. Chances are you just found another way of solving it, and I'm totally cool with that. So du over 2 is the same as dx. So let's replace that. And we're going to get 1 over u times du over 2. This 1 and this 2 basically give me a coefficient of 1/2. So if it is helpful for you, you could write this as like 1/2 the integral of 1 over u du, or even just the dividing by 2 gives you the coefficient of half. And then this is 1/2 the natural log of the absolute value of u plus c. And again, we know that u is 2x plus 3. So we would get equals 1/2 the natural log of 2x plus 3 plus c as my final answer. Let me know what questions y'all have with that. Okay, last one. I'm just moving it up to give myself a little room. I'm going to rewrite this before I even put the u in there as cosine of x and then sine of x squared dx, because I think that makes it a little bit more obvious that this is what we want to have as our u. The derivative of sine is cosine, so that's what we were after there. So I'm going to write this as cosine of x u squared, and then u is just sine. Du dx is cosine. And again, at this point, if you wanted to, you could just replace the cosine with du dx, or you could solve for dx. I think that I replaced last time, so let's solve for dx here. So you get du, so we're multiplying by dx, equals cosine x dx, divide by cosine, and we get dx is equal to du over cosine of x. So I'm going to replace that right there. And we're going to get the integral of the cosine of x times u squared du over cosine x. And those cosine x's are going to simplify for us. So then it's just the integral of u squared du, which is going to be 1/3 u cubed plus c. And then because u is sine, we're going to get this is equal to 1/3 of sine of x cubed plus c. As always, if you see an error or something, let me know. Okay, this one is going to be a little bit less u substitution, but it will still use it in this one part right here. So we've got a derivative, and it wants the original equation, and we're going to find the plus c. So here's what we're going to do. We're going to find the integral of x plus 1 over x plus 2 dx. And because these terms are separated by addition, you can treat them separately. We haven't talked about this too much in class, but if it helps you, you are totally welcome to rewrite it like this. because that really is the case. Like, this part is its own derivative or integral, and so is this. It's its own integral. So this one's not so bad. I can deal with that. It is just using the power rule. So you'd get like x to the 1 plus 1 over 1 plus 1 plus c. Cool, great. I'm not too bummed out by that. We'll get x squared over 2. Here, you might want to use the u substitution. In this case, it's going to feel a little silly, but I'm going to do it anyways. So I'm going to explain that I'm doing this over here. I'm going to write this as the integral of 1 over u dx. And in this case, u, make more room for myself, sorry, u is equal to x plus 2. Du dx is just 1, so that's why this might feel a little silly, but it's okay. We're gonna roll through that. So then I could get that du is equal to 1 dx. All I did there was I multiplied by dx times dx. And then if I divided by 1, I would just get du is the same thing as dx, because here I have a 1, and here dividing by 1 doesn't really change anything. So in this case, I can literally just swap out du and dx. So I can just say this is the integral of 1 over u du, where I literally just swap du and dx. And so I'd get the natural log of u, which is x plus 2 plus c. Okay, so I have this piece of it, this piece of it, plus this piece of it. So let's write that out. We get x squared over 2 plus c plus the natural log of x plus 2 plus c. And I want you to note this plus c is super flexible because it just means that there's some number. So I'm actually going to just combine them. And if you wanted to, you could write this as x squared over 2 plus ln of x plus 2 plus 2c, but c is just some random number, and it's not like I'm specifically solving for it. So weirdly enough, you could literally just leave this as a regular old plus 1c. Okay, so this is our original function. But we're not done, because this asked us to actually solve for the final original and figure out what plus c is. Okay, so we need to use this point, 0, 3, to find the value of c. And what we're going to get is that y is 3 and x is 0. Which will give me, obviously, 0 here. And so we get that 3 is the same as ln of 2 plus c. So then c is going to be 3 minus the natural log of 2. So our final function would be f of x is x squared over 2 plus the natural log of x plus 2 minus 3, or plus 3 minus natural log of 2. Let me know if you got questions. Okay, for a, we're going to use this as our u. So we're going to have the integral of the cosine of 3x e to the sine, we're going to write that as u. I know what I'm doing, don't worry. U dx, where u is the sine of 3x. Then du dx is going to be 3 cosine of 3x. And then this time, we're going to try a little bit different. We're going to divide by 3. And so we need a 3 down here. So we're going to get that the cosine of 3x is equal to 1/3 du dx. And then I'm just going to replace the cosine of 3x, nope, wrong one, there we go, with 1/3 du dx. So I'm going to get the integral of 1/3 du dx e to the u dx. And then we're going to simplify our dx's. I'm going to rewrite this so I get my 1/3 in front, e to the u du. And then our answer is going to be 1/3 e to the u plus c, with u being the sine of 3x. So our final answer is going to be 1/3 e to the sine of 3x plus c. That's part A. B. Oh, buddy. Well, it looks like a lot, but we're going to go ahead and make this inside part here. And the reason I'm picking that is because of the 5. That's really the bigger inside function. So let's rewrite that. We're going to say the integral of x minus 3 times u to the 5th. And we're going to let u be x squared minus 6x plus 4. Then du dx is going to be 2x minus 6. Hey, that works out kind of nicely. See how this is 2 times this thing? So in fact, excuse me, I'm going to choose to just divide this whole thing by 2, which is the same as like multiplying by 1/2. And so I'm going to get 1/2 du dx is the same as x minus 3. And then we're just going to replace that x minus 3. So we're going to have the integral of 1/2 du dx times u to the 5th dx. Those dx's are going to simplify for me, and then I just get the integral of 1/2 u to the 5th du. U to the 5th, just this part right here, would give me the antiderivative of 1/6 u to the 6th plus c. We cannot abandon our 1/2, so that's going to get us 1/12 u to the 6th plus c, whereas u is x squared minus 6x plus 4. Cool. Okay, number 7 requires a little unpacking, but y'all can do this. So it says marginal cost is the derivative of the cost function. So we're going to have some function c, and its derivative, c prime, which is the same as dc over dn, is going to be marginal cost. And we have a formula here for dc dn, where c is the total cost, and n is the number of items produced, given that when no items are produced. So this bit right here is how we're going to end up getting c. So this is basically giving us a point of like n equals 0, so n is 0, the cost is 1,500, and so this is like our x, and this is like our y, so we get the point 0, 1,500. That's going to help us get our plus little c, which is not, annoyingly, here. So first of all, let's get an expression for c. So part A is asking, basically, find the function. So we're going to get the antiderivative of 4n over n squared plus 1. And in this case, because it's all n's, we're going to have a dn. I'm going to let u be this piece right here. So we're going to have the integral of 4n over u dn, which means that u is n squared plus 1 du. Wow, I should make better u's here. Du dn is going to be 2n. My u's and n's look a little too much alike. So then we'll solve this for dn. So if we do that, we're going to get du over 2n is equal to dn. I just multiplied by dn and divided by 2n, so we've got this. So I'm going to now replace this, and we're going to say the integral of 4u over u times du over 2n. So I just replaced dn with du over 2n. Okay, my u's actually simplify. That's kind of cool. I don't think we've seen, well, one of them simplifies. So we're left with the integral of 2 over u du, which is going to lead us to the antiderivative, 2 natural log of u plus c, and u is, so we get 2 natural log of n squared plus 1 plus C. Okay, so that is A. And if we're going to actually get the cost of producing 7 items, we need to know C. Because we could write down at this point that like capital C, which is different than little c. If it helps, you could use like a K or an M or something else here. We need to plug in this. Sorry, I hit the wrong button. We need to plug in this 0, 1500 to this equation. So I'm going to write that out. We're going to say 1500 is the same as 2 natural log of 0 plus 1 plus c. And so we're going to get 1500 minus 2 natural log of 1 is equal to c. So if we want to plug in 7 items there, then we would have, what is c for 2 natural log of 7 squared plus 1 plus 1500 minus 2 natural log of 1, and that gets us, I'm just using a calculator here, and we get about 1507.82 is the cost of those. And then it says sketch the curve and comment on its shape as n increases. So if you're going to sketch the curve, I encourage you go to Desmos, make Desmos do it for you, because it is a very strange looking curve. Here's what it looks like, but make note of the axes here. Like the axes are pretty far apart here. Like we're just 1500, 1450, and it's just very slowly increasing. So that's your curve in part C. Okay, so we've got this water flowing problem, and it is flowing from a tank at the function r of t, and it is flowing into the tank at s of t. So I just graphed them over here so we can kind of get a picture of what's going on. So r of t, we're saying it's flowing from the tank, and obviously we're not looking at the negative numbers. In fact, it actually only wants us to look at 0 through 5. So it's flowing very slowly from the tank, but it's kind of speeding up over time. And it is not flowing in, then all of a sudden it starts flowing in. It's going a lot, and then it's kind of tapering off over here. So we just kind of have a picture of this. So it wants us to find the intervals of time where the amount of water is increasing. So what I would suggest that we do is we actually just make this into a single function, because if we want to know like the amount of actual water, that's going to be equal to the flow in minus the flow out. Well, the flow in is s of t, so we're going to have 10t over 1 plus 2t squared minus the flow out, which is going to be 5 sine of t minus 120. So let's get a picture of that. So here is that image, and notice the entire time it's positive, and because the entire time it's positive, then we can say that the intervals when it is increasing is literally the whole time. So that's your answer for A right there. So then when t is 0, there is 25 cubic meters of water in the tank. So we want to find an expression for t, the amount of water in the tank at time lowercase t. So what they've basically described to us is that this function right here is the change over time of the water, and then they gave us a starting amount of water. So this is basically our derivative, and we need to find the integral. Shocker. So we need the integral of 10t over 1 plus 2t squared minus 5 sine of t over 120 dt. So let's go about doing that. Just like I did in that other problem, we're going to kind of split this into like this half and that half. So over here, we're going to have the integral of 10t over u dt, and then we're going to have minus the integral of 5 sine of t, sine of u, although I'll make it a different u, so we know that we're not dealing with the same thing, dt. Okay, so on this first side, let's deal with this first. In this case, u is going to be 1 plus 2t squared du dt is going to be 4t. Okay, so then dt would end up being du over 4t. So let's get the integral of 10t over u times du over 4t. Those t's would simplify for us, and then we'd get 10 divided by 4, which would get us 5 halves. So we'd have 5 halves integral of 1 over u du, which would get us 5 halves natural log of 1 plus 2t squared plus c on this side. On this other side, we're going to have u is equal to t over 120, so du dt is just going to be 1 over 120. So dt is going to be equal to 120 du. So then we're going to get the integral of 5 sine of u times 120 du, which would get us 600 integral of sine of u du. So we get 600 cosine of t over 120 plus c. And then to piece these two things together, we're not going to forget that this was a subtraction, so we're subtracting the whole thing. So right now we have t of x is equal to that. And then we were given at the very beginning, if you go back to your actual problem, that at t equals 0, there's 25. So that gets us the point 0, 25. So we could then start solving for c. All I've done here is plugged in 25 and 0. So what this will give us is here we're going to get a 0, and then we're going to get the natural log of 1. And actually the natural log of 1 is 0. So this whole thing would be equal to 0. And the cosine of 0 is equal to 1. So we'd have like negative 600 times 1 plus c is equal to 25. So then we get 625 is equal to c. So our final function is actually this one. And the last bit is they want us to find the maximum amount of water in the tank. And so we're looking for the maximum of that original function and when that occurs. So looking at the actual function, that happens at the very end, which makes sense because if you remember way back at the beginning here, what we found was that the original function was increasing the entire time. And if the original function is increasing the entire time, it should end there. And so it wants the value of the maximum, so we just need to get the value of that. So we would plug in 5 to, plug in 5 here, and you will, t of 5 is about 35.35. Okay, cool.